Central expansion sphere packing in a container sphere. Aaron Cattell. August 23, 2025. Abstract. We study a constructive approach to packing spheres inside a larger container sphere. The method begins with a central sphere of radius r, followed by successive shells of smaller spheres tangent both to the inner configuration and to the container boundary. We compute the volume fractions for one shell and two shell packings and compare the resulting efficiency. Our results show that even with simple symmetric constructions, the packing fraction grows significantly as additional shells are introduced, although gaps remain due to geometric incompatibilities. Introduction. Packing problems are classical in mathematics, with sphere packing in Euclidean spaces among the most studied. Traditional approaches emphasize uniform radii and asymptotic densities, whereas here we consider a constructive method where spheres of different sizes are placed in concentric shells within a containing sphere. The guiding idea is to fill from the center outwards, beginning with a large central sphere, followed by layers of smaller spheres. Mathematical model. Let the container sphere have radius r equals 1. We place a central sphere of radius r0 equals r. Around it we arrange m equals 12 equal spheres tangent to both the central sphere and the container. By geometry, each shell sphere has radius r1 equals rr0. 2 equals 1 alpha. The filled volume fraction after one shell is 4. 1 equals 3 pi r30 plus Mr 31. 4. 3 r3. 1. For a second shell, smaller spheres are placed in the gaps between the 12 outer spheres. In an icosahedral arrangement, 20 positions are available. If each second shell sphere has radius r2, tangent to the container and neighboring spheres, the new packing fraction is 4. 2 equals. Results. 3 pi r30 plus Mr 31 plus 20 r32. 4. 3 r3. For alpha equals 1 2, the one-shell construction fills about 31% of the container, while for alpha equals 1 3, where r0 equals r1, the fraction improves to nearly 48%. Adding a second shell increases the density, further reducing the unfilled gap. Figure 1, volume fraction filled versus number of shells in the central expansion packing. Conclusion. The central expansion packing demonstrates how mixed radii spheres can achieve improved F-Illing densities in a container sphere compared to a single central sphere. While even two shells leave noticeable gaps, the packing fraction increases significantly with each additional layer. Future work could explore recursive shell additions, numerical optimization of radii, and comparisons with known dense packings such as face-centered cubic and icosahedral arrangements. This constructive method provides insight into hierarchical packing schemes and their potential applications. References: 1. J. H. Conway and N. J. A. Sloan, Sphere Packings, Lattices and Groups, Springer, 1998. 2. Figure 2. Example of two-shell packing for alpha equals 1/3, one central sphere, 12 in the first shell, and 20 in the second shell. 2. T. C. Hales, A Proof of the Kepler Conjecture, Annals of Mathematics, 162, 310651185, 2005. 3.